Hey everyone! Welcome back to our 3D printing series. Today is day 3 and we're diving into one of the most widely used and beginner-friendly 3D printing methods, Fused Deposition Modeling, or FDM. Let's get started. Fused Deposition Modeling, or FDM, is an additive manufacturing process where a 3D object is built layer by layer using melted thermoplastic filament. The filament is heated and extruded through a moving nozzle, which deposits the material in precise paths based on a digital 3D model. As each layer cools and solidifies, the next is printed on top, slowly building the object from the ground up. It's a cost-effective and widely used method for everything from rapid prototypes to functional end-use parts. Now let's take a closer look at how FDM 3D printing actually works step by step. Step 1. Design phase. It all starts with creating a 3D model using computer-aided design software like SolidWorks or Tinkercad. This model defines the shape, size, and structure of the object you want to print. Step 2. Slicing. The model is then sliced into hundreds or thousands of thin horizontal layers using slicing software such as Cura. The slicer also generates G-code, a set of instructions that tells the printer exactly how to move and when to extrude material. Step 3. Material feeding. A thermoplastic filament such as PLA, ABS, or PETG is pulled from a spool and fed into the heated printhead. Step 4. Melting and extrusion. Inside the extruder, the filament is heated to its melting point and then forced through a small nozzle. Step 5. Deposition. The nozzle moves along the X and Y axes, depositing the melted material precisely onto the build platform, layer by layer, following the path defined by the G-code. Step 6. Solidification. As the material is extruded, it quickly cools and solidifies, forming the first layer of the print. Step 7. Layering. Once a layer is completed, the build platform lowers slightly along the Z-axis, and the next layer is added on top. This layering process continues until the full 3D object is formed. Step 8. Post-processing. After printing is finished, the part is removed from the platform. It may undergo light post-processing, such as cooling, support removal, or surface finishing, depending on the application. To help you better visualize this process, let's take a look at a short video demonstration. Fused Deposition Modeling supports a wide range of materials. These include both basic filaments and advanced engineering-grade options. Let's start with the most commonly used materials. Polylactic acid is biodegradable and made from renewable resources. It's easy to print and ideal for prototypes and educational models. ABS, or acrylonitrile butadiene styrene, is strong and impact-resistant. It's suitable for functional parts but can warp if not printed under controlled conditions. PETG, or polyethylene terephthalate glycol, combines strength and flexibility. It resists moisture and chemicals. This makes it a great choice for containers and mechanical parts. TPU, or thermoplastic polyurethane, is flexible and rubber-like. It's perfect for items that need elasticity, like phone cases or wearable parts. PVA, or polyvinyl alcohol, is a water-soluble support material. It is used in dual extruder printers to support complex structures. Once printed, the PVA dissolves in water. This leaves behind a clean, high-quality final print. Now let's talk about advanced FDM materials. PC, or polycarbonate, offers excellent strength and heat resistance. It's commonly used in automotive and industrial applications. Nylon, also known as polyamide, is tough and wear-resistant. It's often used for functional parts in engineering. Carbon fiber reinforced filaments are composites like carbon fiber PLA or carbon fiber PETG. They offer higher stiffness and strength for performance parts. Polyethermide and polyether ether ketone are high-temperature plastics. They are used in aerospace, automotive, and medical industries. These require specialized industrial-grade 3D printers. With this wide variety of materials, FDM is suitable for everything, from simple models and educational use to industrial-grade parts and real-world applications. To better understand how PVA works as a support material, we'll now move to a short video. It demonstrates how dual extruder 3D printers use PVA to build complex structures, and how the supports dissolve effortlessly in water, leaving behind a clean and precise print. Fused Deposition Modeling, FDM, is one of the most accessible and popular 3D printing technologies today. It offers several advantages, making it ideal for beginners, educators, and professionals. FDM printers are affordable, with budget-friendly machines and filaments. They are easy to use, requiring minimal setup and maintenance. Even first-time users can start printing quickly. A wide range of filament types and colors are available, allowing for creative freedom. FDM is excellent for rapid prototyping, turning digital models into physical objects within hours. It's also a clean process, no messy resins or hazardous chemicals, making it safe for homes, schools, and offices. However, FDM has some limitations. Print resolution is lower compared to resin printers with visible layer lines. Materials like ABS may warp without proper temperature control, though a heated bed and enclosed chamber can help. FDM is limited to thermoplastic filaments and cannot print with metal, ceramic, or resin. Fine details may be difficult to achieve due to nozzle size. Despite these drawbacks, FDM is highly versatile. In engineering, it's used for prototyping and functional testing. In education, it supports hands-on learning in STEM and art. In healthcare, it helps produce anatomical models for training and surgical planning. Makers use FDM for custom gadgets, and it's common in producing consumer items like toys and phone stands. FDM is a practical, cost-effective tool that continues to drive innovation across industries. One inspiring real-world example of FDM 3D printing is the e-NABLE community, a global network of volunteers who use 3D printers to create prosthetic hands and arms, especially for children born with limb differences. Traditional prosthetics are often expensive, hard to access, and difficult to customize, particularly in underserved regions. e-NABLE addresses this by using affordable FDM printers and polylactic acid, or PLA, to produce functional prosthetics at a fraction of the cost. Volunteers use open-source designs that can be easily scaled to fit the user, and the printed parts are assembled using simple tools. Each device typically costs only $20 to $50 to produce, and many are donated free of charge. To date, over 10,000 prosthetic devices have been delivered worldwide, giving children greater independence and confidence. This project not only improves lives but also encourages STEM learning, as many volunteers are students, teachers, and makers gaining hands-on experience in design, engineering, and community impact. That brings us to the end of Day 3 in our 3D printing series, where we explored Fused Deposition Modelling, or FDM. You've now seen how the technology works, the materials it uses, its advantages and limitations, and how it's applied in real-world scenarios like the e-NABLE project. We hope this session helped you understand why FDM is such a powerful and accessible tool in modern manufacturing. If you found this video helpful, please like, share, and subscribe to the channel. Don't forget to hit the bell icon to stay updated with upcoming episodes. If you have any questions or thoughts, feel free to drop them in the comments below. Thanks for watching, and we'll see you in Day 4.